Wait, oh, P1, P2. Yeah, I want 1, 2. 1, 2, 1, 2, 1, 2. And what was the next one was what? P what?
P2, P0.
Okay, P2, P0. So I'm going to say that these, line segments essentially are my basis elements for gamma 1. So let's think about partial 1 is a mapping from where to where? It's a mapping from C1 to C0, right? So I can calculate what's the matrix of the gamma of partial 1 map with respect to my, say, gamma 1 comma gamma 0 matrix. This is my usual linear algebra notation, And so that is the, so we calculate partial 1 acting on, the first basis element in gamma 1, which is P0, P1. And then we're supposed to calculate the coordinate with respect to gamma 0. And then I calculate what's partial 1 acting on the next basis element, which is 1, 2. And then I'm supposed to calculate the coordinate vector of that with respect to the gamma 0 coordinate chart. And then I calculate what's the gamma partial 1 acting on P2, P0. And then I calculate coordinate of that. And so that, we just worked, we know, I guess I'm just redoing it, I'm sorry, but, so this one is, if I was smarter, we could, anyway, once we get done with this, maybe you can go back and look at the formula and read the matrix straight off of it, if you're comfortable with things, but I'm just gonna do it explicitly here. So this is P1 minus P0, gamma coordinate of that, and this one is P2 minus P1, the gamma 0 coordinate of that, P0 minus P2, the gamma 0 coordinate of that. Now, what are those? Well, that depends on the ordering of the basis, you see? The first one is the 0, the 0th one is 1, the first one is 2, the second one is the third, right? So this is minus 1, 1, 0. This, 0, minus 1, 1. That, 1, 0, minus 1. So there you go, that's the matrix. And we have a theorem of linear algebra, of course. The dimension of the null space of the matrix is the dimension of the kernel, right? The dimension of the column space of the matrix is the dimension of the image. And this is 221, right? Like, we can just do this stuff. So what do you guys see anything here? Is this invertible?
No.
No. What's that?
I said, let's go.
Let's go. All right, fine. I'll do a row operation then.
I just row operated in my head.
You just row operated in your head? And how'd that feel?
Felt nice.
It felt nice?
See that inversion right there in the second two rows.
So there you go. There's the standard fare. The reduced to echelon form clearly reveals that the rank of the partial 1 map, which is of course the dimension of the image of the partial 1 map, is equal to, how many column vectors do we have? What's the dimension of the column space here? 2. On the other hand, the nullity of partial 1, which of course is the dimension of the kernel of the partial 1 map, is 1. Let's see here. It's fine. All right.
Just wondering where we get like the n plus 1 thing going.
The m plus 1? Oh, okay, so let's review. So gamma 0 is a mapping from where? From C0 just to 0, right? So what's this tell us? the dimension of the kernel of, did I say gamma 0? I meant partial 0. Good grief. The dimension of this guy is 3, right? All right, what else can we think about? How about boundary 2? That goes from C2 to C1, right? But what is C2? This is 0, right? So what does that tell us about the dimension of the kernel of boundary 2, and what's the dimension of the image of boundary 2?
Kernel 0.
Mm-hmm. How about the image?
1.
No.
3.
You're inputting 0. What can you output? It's a linear transformation, so
Okay.
it's 0, yeah. I think we have everything we need to calculate the Betty numbers, right? Should we let's try to put it together? What do we got? Beta 0, the 0th Betty number is what? I've lost track of my toys. Dimension of kernel of the 0 map minus the dimension of what? The image of the one boundary, right? Which was what? So 3 and 2. So we get 1. Beta 0 is 1. How about beta 1? So there we're looking for the dimension of the kernel of the boundary 1 map minus the dimension of the image of the boundary 2 map, which is what? 1 minus 0, which is 1. See ya. So there we go. Everything higher than that, everything's 0. Like the image and the kernel, they're all 0 past where we are. So we can summarize this. So we can write this. The mth homology group of the circle, by the way, is equal to the mth homology group, yowzers, the mth homology group of the triangulation of the circle, and we just calculated that. And what we calculated revealed that it's either the real numbers themselves, the one-dimensional vector space for m equals to 0 or 1, or it's 0 if m is, greater than or equal to 2.
And what kind of a morphism was V? When we started out.
V?
V to go into the
V.
triangle.
Oh, that's a homeomorphism in principle from the triangulation. And the point is that by definition that we have a triangulation of a space if and only if there is a homeomorphism from a simplicial complex to the space. And the claim is it's just geometrically evident that that triangle is homeomorphic to the circle. But we've calculated the homology groups of the triangle through this algebra, linear algebra. And that reveals that these are the homology groups of the circle. So the Betty numbers are 0 and 1. Yeah. I think it would probably be helpful for you guys to see one more example, right? So let's do that, and then we'll be done. Let's see here. Bagada.
So that's called the homology?
Yep, this is the homology group of the space. Let's see, can I don't want to erase. Well, let me see, let me be careful here. Maybe I can. The next example is instead of doing the circle, now he wants to do the disk. All right, so we might be able to not erase a lot of this and get stuff from it, right? So what's the difference if we example 5.5, I guess it is. Example 5 point, does he call it 5? Yeah, 5.5. So what's new?
Shade.
We shaded in, right? Now we got a 2 chain, right? Mm-hmm. But we haven't added anything. Like the cool thing about this. So now it's a good grief. Triangulation of the 2 ball, also known as the disk. You know, he calls it D2. But he also would call it B2, I think, but whatever. It's not bad. It's not bad. So the 0 chain's the same, 1 chain's the same, 2 chains, we got a 2 chain, all right. So the set of 2 chains, now no longer 0, now we've got well, it's kind of boring though. It's just like, you know, lambda times the 0, 1, 2, you know, such that lambda is a real number. There you go. That's your 2 chains, space of 2 chains. It's one-dimensional, right? So I don't think the calculations change. Where would they change? Everything would be the same. Yeah, so we need to be careful with our let me circle. I'm going to circle this to remind myself that this is where I need to change it. I need to change that. All right. And I'm going to yeah, let me move the camera back over here. Isn't this nice though? Like it's very concrete, calculational.
Well, what's it exactly telling me?
Oh, what does this mean? Well, that's a good question. He said that the mth homology group counts the number of. He said the Betty number counts the number of holes. Let me read what he said exactly. See if you can make sense of it. Oh man, where'd it go? He says, as we shall see, beta mk basically counts the number of m-dimensional holes of k, quote unquote. So there's one 0-dimensional hole in S1. I don't know what is that? I'm not sure that sentence really has any meaning for m equal to 0. But for 1, okay, so a circle has 1, wait a minute. I have a question mark next to that sentence. I don't know what that sentence means. So, but maybe when we calculate this next thing maybe perhaps calculating the homology for the disk will make us feel a little bit better.
It seems as though, oh yeah, let's just do it.
Okay, so C2 is no longer 0. Yeah? So we can no longer say that the boundary and the image of these are 0. We actually have to calculate. We need to actually work it out, you know? So, I think I can do it here, right? Dimension of gamma's, dimension of partial 0 is still 3. I'm going to erase it, okay? This is still true. We didn't change that. It's not related to 2 chains at all. Okay, so as we think about the matrix of the partial 2 now, right? Now we have to think about it. So I would do that with respect to, let's say, the input is gamma 2, the output is gamma 1, right? And so here's the way that works. We take gamma 2 of the first thing in the, oh, well, there is only one thing, isn't there? Right? There's what? There's this. I'm saying gamma 2 is going to be just the set containing the, that's my basis, okay? It's one-dimensional, so there's just one thing in it. So we're only going to have one column here, you know? And that one column, we're supposed to calculate the gamma 1 coordinate of it. All right, so that's the gamma 1 coordinate of what we got here, P1, P2, minus P0, P2, plus P0, P1. All right? And that is explicitly what? A 3 vector. And so my basis gamma 1 is up here. I got what? I got the first thing in the basis, I got minus one of them. The second thing in the basis, excuse me, this one is not right yet, right? So to figure out the coordinate vector, technically I probably should put a plus here and swap the numbers. There you go. So that gives me, that puts a 1 in the third spot, right? And this one, wait a minute. Oh, anyway, that was a 1. I can't do math. So that one's first. Sorry, just a second. I'm processing. So one of those, and after I adjust the sign, it says 1, 1, 1, right? I mean, it doesn't really matter. Once you have, I'm just quibbling, but it's obvious then. What's the, you know, what's the dimension of the kernel of the boundary 2 map? What's the dimension of the image of the boundary 2 map?
2 and 1 would be 0 and 1. The image would be 1.
All right, we're going to have to come to a consensus on the other one. So kernel.
Well, the kernel has to do with the set being mapped, right?
Mm-hmm.
And the set being mapped is only one-dimensional.
That's right.
And
Mm-hmm. So, well, we can fall back if we're uncertain, and I'm not saying that we are uncertain, but here's the, you know, the dimension of the boundary 2 map goes from where to where? From, so we have the dimension of C2 equals to the dimension of the kernel of the map plus the dimension of the image of the map, right? This is how we can be sure. We know, it's clear that this is 1 from the calculation, right? But this is also 1. And for that reason, this must be 0. So now we can go back to the calculation of the first Betti number, right? And what is it? This was 0 before, but now it's 1, right? Now it's 1. And as such, we now have 0 here, right? So apparently, we still got beta 0, but the beta 0 calculation didn't change because that involved maps that aren't altered at all. from our previous example. But now we've lost that the first homology group is R. Now it's 0. There's, I think, one other thing to consider here. What about, maybe there's something to think about with beta 2 now, right?
Well, then we just have the same situation we had for, oh wait, never mind.
I mean, let's work it out. What's beta 2? Can I erase, I think I can erase this stuff, right? We don't need to, we're done with this. Uh-oh.
No, we have the dimension of the kernel of what, del 2.
So that, yeah, the dimension of partial 2, oops, my bad. Kernel partial 2 minus the dimension of what? The image of partial what?
So partial 3 is just going to give us 0.
Right, yeah, partial 3 is from C3 to C2, and partial 3 is identically equal to 0 because C3 is 0. So you're right, it's the same situation we had previously, but now this is 0. And the dimension of, oh, but the dimension of kernel 2 is also 0. So it's I guess it's slightly different. I mean, we should check that it's 0 though. There's something to check there. Now past that, beta 3 and higher automatically 0. So yes, this is the homology group not of S2, S1, but you know, if you like D2, I could say B2. It's the disk anyway. Try and disk. There we go. So the disk doesn't have the same homology as the circle. There's no hole in the same way in a disk as there is in a circle. I mean, there's a hole in a circle, right? That hole is absent in the disk, right? It's been filled in, and that's why we don't have 2 coefficients non-zero.
But the dimension of the, so there's a lot of zero-dimensional hole there.
Yeah, I think the significance, well, let's see if I can skip ahead. So, do you guys know what the Euler characteristic is? So we talked about the Euler characteristic in the manifolds course. I think I talked about the Gaussian
curvature.
Gauss-Bonnet theorem. The Gauss-Bonnet theorem relates the integral of the Gaussian curvature over a surface to the Euler characteristic. And here we also learned that you can calculate the Euler characteristic by taking the alternating sum of the what is it here? What's the alpha j alpha? So you can count if you count the number of simplices, well, he's got a formula for calculating the Euler characteristic from taking an alternating sum of the number of j faces. So that's one side of things. Like you can count the number of edges, the number of holes. I mean, the number of vertices, the number of edges, the number of faces. That you do this alternating sum of that to build up the Euler characteristic. But on the other hand, it's also equal to the alternating sum of the Betti numbers. So like the formula is like the Euler characteristic of space is equal to the sum j equals 0 to the dimension of the space of -1 to the j beta sub j. So like, since we know So we could calculate like what's the Euler characteristic, for instance, of the disk, right? What would the Euler characteristic be of the disk, or as I'm calling it, B2? We do beta 0, right? Minus beta 1 plus beta 2. Well, yeah, plus beta 2, but that's what you said is 1? Yeah, it's 1, right? Cool. What's the Euler characteristic of the circle? Apparently it's, I think you said 0? I think you're right, yeah. I've erased that, but we had beta 0 and beta 1 were both 1. So Euler characteristic of the circle is 0. Now in your homework that I've asked you guys to do, you will calculate the homology groups of the two-sphere. So what you're going to do in your homework is you're going to work out this example for the tetrahedron, being the simplicial complex. So there you've got non-trivial, you've got a 3-chain, which is the whole tetrahedron, right? So let's talk through it here before you guys have to face it alone. As I think about exercise 5.3, which is triangulating the two-sphere, if you think about the tetrahedron being the triangulation of it, you've got one 3-chain, so the C3 is one-dimensional. C2, well, for the tetrahedron, you've got 1, 2, 3, 4 faces. So your C2 of the triangulation is 4-dimensional. There's the 4 faces of the tetrahedron. And then what about C1? How many edges do you have in a tetrahedron?
6. Counted it the other day.
6. So that's a 6-dimensional space. So I didn't do that in class because it's going to give you so you're going to have matrices that are like, involving these numbers. So you might have a 4x6 or a 6x4. I can't remember which way the numbers go, but but they tell you the answer you're looking for, so that's helpful. Yeah. Now, if you and I've given you guys some other homework problems that are really, really interesting. I'm just going to skip ahead a minute here. So if you can, yowzers. He later in chapter 6 introduces a so-called de Rham cohomology, and there he relates de Rham cohomology, which has to do with differential forms, to homology, which we've studied today, and there is a, like, corollary 610 tells us that the de Rham cohomology of M is in some sense the same as the homology of M. For a fun application of homology and cohomology to electric circuit theory, see Appendix G. That's wild to me. I have never studied that stuff. I am morbidly fascinated with what on earth that. I'm afraid if I ever study it, I'll start teaching it, and then students will be annoyed. So, but I like this though, because this is a really cool example of quotient vector spaces, how basic linear algebra calculates something pretty interesting. And it's also like, it illustrates well why we call it algebraic topology. You're actually using algebra to calculate something non-trivial in a topological sense, because so homology groups are a topological invariant. If you had a homeomorphism from one topological space to another, you can prove that the homology groups will be the same for both. So if I can calculate the homology groups for a space and show that they're different than a space I'm interested in, that would disprove that the space I have is homeomorphic to the space I'm interested in. you know, just like with homotopy. And I do think there's I was trying to find the interconnection. I want to say the zeroth, I shouldn't say, I don't know. I feel like there's got to be some connection between, I shouldn't even say. You guys will figure these things out in due time. That's what grad school's for, so. Thanks, guys. Whew. Goodness gracious.